Okay, so in Unit 4, this is all about function analysis. So in 4.1, we're going to discuss a few of the important theorems that talk about some ideas you might already know in your mind, but this will make them formal. The idea with the theorems is you need to show that you've tested for the necessary conditions that guarantee what the theorem states, okay? So these are typically free response, 1-point questions. Some of these theorems can also be multiple choice as well. All right, so we're going to call these existence theorems. So existence theorems means it's not going to give you an answer, that it just tells you about an idea that is here. And so we did this back when we did limits with the intermediate value theorem, the IVT. That was the intermediate value theorem for limits. This is now the intermediate value theorem for derivatives, okay? So it just tells you, some of the existence theorems, they just tell you that a solution does exist. And these are used a lot in the real world, especially with like running, driving, because of the ideas that they cover, okay? We don't really use these theorems in real world problems in calculus. We use them to analyze functions, okay? So remember, most of these problems you would be analyzing without a graphing calculator, okay? So the first one is the intermediate value theorem for derivatives. So I always call it the IVT for derivatives, okay? So the intermediate value theorem, I like to think of the word intermediate as middle to help me remember, what does the IVT really tell me, okay? So the IVT, it says if you have a continuous function, which remember, what does continuous mean? It means that there are no holes in the original curve, and that you can substitute all x values and you should get a y value, okay? That's the idea of continuous, okay? It's the original function, all values are defined. So you have a continuous function, and it says that if you have an x value of a and an x value of b, okay? So this is an interval. So on a to b, that interval, then it says whatever this y value is, so this y value is f of a, and whatever the y value at b is, so that's f of b, f of a. If you have a continuous curve, then every value from here, f of a, to f of b, all the y values will have at least one point covered in the interval a to b, okay? So it says, like, let's just take numbers. So let's say that this y value is 1, and this x value is 2. And then this y value is 10, and this x value is 8. So what it says is on from 2 to 8, so on 2 to 8, all y values from 1 to 10 will be represented at least once, okay? So that's what it means. So a lot of times what happens on functions is they want you to justify that there was a solution. Well, a solution would mean that it was equal to 0. And so what you usually have to prove is that one of your y values was negative, one of your y values was positive. So then it's guaranteed somewhere on that interval, there would have been a solution. You won't be able to find it, but it's just guaranteed that there will be at least one solution. So that's kind of the application for function analysis for the IVT. That's it. So that's it. So in order to use the IVT, you will have to state that the function is continuous. You'll have to state the two endpoint y values and then just put it all together with the statement. Okay? So let's look at number 1. I've got 2 examples of this. Show that this function has at least one root, so that means equals 0, between x equals 1 and x equals 4. Okay, so what we're going to say is that f of x is continuous for all, and so this is the symbol for all, but I'll write it out. So it's like a big V, it kind of like dips down for all x values. So you don't have to prove this to me. You don't have to tell me that it's a polynomial. You are just making this statement to show the reader and the teacher that you know the function is continuous, and that's the condition that is needed for the IVT. All right? So that's the idea. It's just a little statement. Don't go proving to me all polynomials are continuous because blah, blah, blah. Nope, we don't need that. All right, so then what we're going to do is we're going to say, oh, well, if it's continuous from x to 1, and we'll also say on -1 to 4, because that's really what we care about. So the function might not be continuous for all x values. So if it's on your restricted domain, you would just say it for that restricted domain. On this problem, it is true for all, so you can say it either way. All right, so what we're going to do is we're going to find f of -1, and we're going to find f of 4. Okay, and so typically you wouldn't have a calculator for this, so it's going to be a nice polynomial or something that you could do by hand. So we're going to find that y value, and I'm just going to write it out. You don't have to show this part, but I'm showing this to you. So what do we get? -2 minus 8 minus 5 minus 2. So 10, 7, so equals -17. And if I plug in 4, so what do I get? 64 times 2, 16 times 8. I'm going to do a little bit of math up here. What's that? 8, 4, 128. So we get 18. Okay, so basically, let me show you a picture, and you don't have to draw this picture for me. But basically what's happening is at -1, -17, I have a dot. And then at 4, 18, I have a dot. And we know our curve is continuous, so we don't know what it looks like. It doesn't matter. So because our y value goes from -1, a negative, to a positive, somewhere it would have had to cross the root at least once. It could have crossed more than once. So all you need to say is since f of -1 equals -17 and f of 4 equals 18, and we have this, and f of x is continuous on -1 to 4, you would say by the IVT, at least 1 f of c equals 0. Okay, or you could say there is at least one x value such that the y equals 0. Okay, but you want to state the conditions. So the conditions are it's continuous and that your y values change signs. So this would be your statement on a free response for 1 point. Okay, so that's it. We don't know where it is. We're not finding it, but we're just guaranteeing that it does exist. All right, so I always like to throw trig in because I think it's a good trig review. So this says, example number 2, does the IVT guarantee roots? So remember, roots mean that your equation equals 0 for f of x equals all of that on 0 to pi. Okay, so now what we need to think of is our function continuous? And this is not a graph that I would expect you to know. But what you do know, let me talk you through this, and then I'll do the actual work, is if we have cosine, I know the cosine graph looks like this. It is continuous. And I know sine looks like this, and it's continuous in both directions, okay? And so if we would, and this just moves the graph left and right, this shrinks it. So it just makes it like, it actually changes the period. So instead of 1 cycle, you have 3 complete cycles. So this changes the frequency. But it doesn't change any holes or anything, okay? So if I would take, and this 5 makes it taller. So if I would move things left and right, shrink them, stretch them, and multiply them together, am I going to get any wholes? That's what you're kind of thinking of. And you're like, well, no, I would just have numbers being multiplied by numbers, subtracting numbers. They could be positive or negative. We don't care. So all of this is continuous. And then we're going to subtract some number. Well, if I take a number and I subtract a number, I'm going to get a number. Is there any time you wouldn't get a value? And so the answer is no. So what we know is that f of x is continuous. It's for all real numbers, actually, for continuous for all real numbers. But it really is on 0 to pi. Okay, so we're going to state that. But does it guarantee a root? So what I want to do is I want to plug in what's f of 0 and then what's f of pi. Because I don't know that it's going to go from positive to negative. That's what we want to check. If it goes from positive to positive, then it's not guaranteed. It could have a root, but the IVT doesn't guarantee that it has a root, okay? We'd have to do the actual math to get the root, if that makes sense. But I do want to do trig because I think we just need continuous trig review. How do we do all these problems? So I'm going to erase this so I can actually see the problem. All right, so if I plug in 0, I'm just going to write it all out. Okay, so we get 5 cosine of pi times the sine of 0 minus 0. All right, so now we need to go back to our wave. So sine, that's at 2 pi, that's at pi, that's at 0. So the sine of 0 is 0. And 0 times anything actually gives you 0. So 0 minus 0 does give us 0. Okay, but let's review cosine, just in case that one wasn't 0. So cosine, we've got, that's pi over 2, this is pi. So the cosine of pi is -1. So we'd have 5 times -1 times 0. Okay, which is still 0 minus 0. Now let's plug in pi. So I'm going to change colors. So if we plug in pi, I lost my, there we go. I would get 5 times the cosine of pi plus pi times sine of 3 times pi minus pi. So 5 cosine of 2 pi. Now, sine of 3 pi, remember, every 2 pi it repeats. So that's really just the sine of 1 pi because we want to subtract 2 pi off of that. All right, we're going to use our waves. So cosine of 2 pi is really the start. So the cosine of 0 is 1. The sine of pi is also 0. All right. So we get that times that times that. So 0 minus pi. So we get equals negative pi. Okay. So what happens, and let's give a picture just in case you're not sure, is at 0, 0, and then at pi, I'm at negative pi. Okay, and we know our graph is continuous. So it could look like this, worst case scenario. And so all it says is that, does it guarantee roots on this closed interval? Remember, a bracket means you can include the endpoints. Well, because I know it starts at 0 and that is on my interval, I'm guaranteed at least one root. Now, this curve could go up and down. We don't know. But I'm guaranteed at least one root at 0, which is on the interval that they want. So we're going to say yes. Okay? By all of this work. All right, so one of the applications, because we just want to know that you hit all the values in between, it's just like when you're driving or people for heights. Like if you were born and then you're 6 feet tall, at some point were you 5'3"? Yeah, I mean, we don't know when. If you're driving at 50 miles per hour, were you at some point driving exactly 34 miles per hour? 38 miles per hour? The answer is yes. Or like if you slow down, would you be driving 5 miles per hour at some point when you slow down? Yes, because you're going to get to 0. So that's one of the real world applications. Okay, so let's move on to Rolle's theorem. So Rolle's theorem it's named after Michael Rolle, but it does use calculus, okay? The IVT, that was just really algebra that it used. Rolle's theorem is going to use algebra and calculus together, and it has a totally different idea. So what it says is you have 2 conditions. This is differentiable is condition number 1. You have to show. And it is continuous on the closed interval, which means you have to also have values at the endpoints. So show this also. Okay? Not in that order. Usually you show it's continuous and then you show it's differentiable. Remember, what does differentiable mean? It means that you can take the derivative and then substitute all values. Substitute all values. That's really what it means. Continuous means you can use the original, has all values. The original function has all values. Okay? And when you do differentiable, you don't have to include the endpoints. So that's why it says it's continuous on the closed interval for the original and differentiable on the open interval, not including the endpoints, because the endpoints technically have tons of tangent lines if you just stop them there. So that's why we don't care. So then the third part you also want to show. So this is what Rolle says. It says if you have 2 y values that are the same, so like here's f of a and here's f of b, okay? Actually, let me just draw it on its own thing. It says if you have a graph where here's a and here's b, so f of a and f of b are the y values. So let's take this y value and this y value, and they want to be the same. Well, if my curve is continuous and is differentiable, remember that means I have no sharp points, then there exists at least one number c, which is really an x value, on the open interval, such that the derivative equals 0. So what does that mean if your derivative equals 0? It means it's horizontal tangent line. So continuous, I mean, I can look like this, okay? So where I would have a horizontal tangent line would be right here. That's horizontal, and I actually have another one right here, okay? This curve that I drew had 2. So horizontal tangent line. Now, what you really notice, and this is coming, so I'm working you towards it, is that wherever you have a horizontal tangent line, we kind of talked about this before, is you kind of have a little low or high point. It's a max or a min. So that's going to be a pretty important rule, okay? And so that's all we know. If we have 2 y values, didn't you have to have a higher or low point at some point if it was continuous and differentiable? Like you can have tons of them. And there are some questions that I get in class about this, but I'm not going to go through all the scenarios, okay? So let's look at our first example for Rolles. So they give us a graph, and then they also give us an equation. So it says show, so this means mathematically, show that Rolle's theorem holds between the 2 x-intercepts, so where it crosses the x-axis. Okay, so right here, of this function. Okay, so on paper, you do have to show that the premises of Rolle's was true. So is f of x continuous? Well, do I have any holes on this polynomial? No, so f of x is continuous. You just write that, okay? And I'll just say for all x, because it is. Differentiable. So can I take the derivative? So I'll just do it. You can do this in your head. You don't even have to show this. And then can I plug in all the x values I want into this derivative? Well, yeah. So f of x is differentiable for all x values as well, okay? You don't have to show the derivative. You just have to state that you've checked those conditions. So I just draw little check marks. And then the third thing is you have to show that f of, what is that, -3 equals 0, and f of that one's at 4. So, okay, f of -3 equals f of 4. So we've got our two y values that are the same. Okay. So then it says somewhere between these two green dots, you had to have a high or low point. So we showed that all of these. So by Rolle's theorem, there exists at least one x value such that f prime of c equals 0. Now, we can find it. If we take our derivative, set it equal to 0, because that's our derivative, we can solve this. So 2x equals 1, divide by 2, x equals 1/2. So I could say at x equals 1/2. Okay? And it's about right there. We have a horizontal tangent line. So now, see how we use calculus? So we are going to be able to find the derivative, set it equal to 0, and solve. Okay? All right, let's try another one. Sometimes they give you a picture, sometimes they don't. So find all values between the non-zero x-intercepts for which Rolle's theorem holds. Okay, so we don't want, so don't use these because it says non, oh, sorry. Let me erase this. So the non-zero x-intercepts. So this is an x-intercept, this is an x-intercept, and this is an x-intercept. So this is the 0 x-intercept, so these are the non-zero. So I'm going to write this for you. So non-zero and myself. Non-zero. So we want to go, we don't know where those are, so that's why they didn't name them. Okay, so we want to say, we're going to call this A, and we'll call this, let's say C. All right. So first, f of x, it's a polynomial, and I don't have any holes. So f of x is continuous. And if I could say on A to C. I should make that capital A. There we go. Now, derivative, I don't have any sharp points, but I can take the derivative and plug in all values. So f of x is differentiable because I can take the derivative on the open interval. If you mess up these brackets, the AP won't take off any points, just so you know. And then the last thing is we want to say f of A equals f of C. Sorry, I don't know why I changed my f's. There's no reason. And I don't even have to say that it's 0. Okay, so 1, 2, 3. So now we're going to find them. So f prime is 6x, just a power rule, minus 4x cubed. I'm going to set this equal to 0. You want to show that on your paper. We'll factor out a 2 and an x. So 3 minus 2x squared. Zero product property, so 2x equals 0. 3 minus 2x squared equals 0. So divide by 2. Add 2x. Divide by 2. And then take the square root. When you take a square root, it's plus and minus. Now, you don't have to rationalize this because you're just finding it. So this would be the positive root 3 over 2. Make sure that's in the root. And this would be, sorry, I said that backwards. This would be the positive. And this was 0. And that's my max, max, min. Okay. So we've got, this said find all values. So we've got 3 because we have 2 max and 1 min. All right, let's try another one. I just thought I'd bring a different function. These can be any kind of functions, any kind of derivative rules. They're usually the simpler ones, but they're not always power rules. So find the values of C guaranteed by Rolle's theorem for this function on that. And look, there's no pictures. So what I notice is when we have a denominator, are we continuous? Well, the only value we can't use is 0, but that's not on our interval. So f of x is continuous on 1/2 to 4. Okay, I just said it. Our derivative, well, let's find out. So if I have my original, I'm going to write these as power rules. I don't want to use a quotient. So 4x to the negative 2 minus 9x to the negative 1. So our derivative would be a power rule, negative 8x to the negative 3 plus 9x to the negative 2. I'm going to write that nicer so I can tell. All right, and I know I can't have 0. Well, that's not on my interval anyway. So f of x is differentiable on 1/2 to 4. Okay, so then I want to plug in what is f of 1/2 into the original, remember? So it's 4 over 1/2 squared minus 9 over 1/2. So 4 over 1/4 multiplied by the reciprocal, so that's 16, minus 9 multiplied by the reciprocal, so minus 18. So negative 2, so f of 1/2. Then I'm going to plug in 4. So f of 4, 4 over 4 squared minus 9 over 4. We have 4 over 16 minus 9 over 4. I'm going to get a common denominator. Times 4 times 4. So I get, I'm running out of room. Let's, oops, move this up. 4 over 16 minus 36 over 16. So 4 minus 32 is negative 32 over 16, which is negative 2. All right, so f of 1/2 equals f of negative 2. Sorry, 4. So if this wasn't true, if these weren't the same, then you would say Rolle's theorem fails because one of these 3 things is not true. So on the quiz, I might give you a problem and say, can you use Rolle's or which of these fails? Does that make sense? Okay. So here I'm just showing you how they work because we have a lot of theorems to go through just to save time. So we already know our derivative and we're going to set it equal to 0. So now we can take our derivative and find it. Well, I'm going to add this to the other side. Because this is a proportion, this is the only time you're allowed to cross multiply. So 8x squared equals 9x cubed. We want to get everything to one side. I know it seems like we're going backwards, but we need to get rid of the fraction. That's why we did this. We're going to factor out x squared. Set them both equal to 0. Take the square root. This would be 2 answers. It's just a double root. And then add 8 and divide by 9. Now, Because of our domain restriction, we can't even have 0 anyway, but it wasn't in our domain because of the original fraction. So our xc value is this x value. 8/9 does fall between 1/2 and 4. So we found it. Okay. All right, one more theorem. So the mean value theorem for derivatives, because there'll be one for integrals. So that's why I always name these. So the mean value theorem, think of the word mean as average, because that's going to be part of the concept. For rolls, I kind of think of like you're rolling down a hill. A hill is a max or a min, okay? Slope is 0. So the mean value theorem, MVT, the idea is on the graph. So the idea says if we have an endpoint from A to B, so this is our interval, these are our endpoints, and then this is our curve, okay? The idea says that if we take the slope of the tangent line and we take the slope between the endpoints, okay? So we take this slope. I'll make it purple. Well, the slope between the endpoints is called the secant line. Okay, so it uses the endpoints. And we set them equal to each other, that somewhere on our curve, the slope of this secant line has to be the same as the slope of the tangent line. So, same at C. Somewhere it has to be the same. We don't know where until we actually do the calculus and the math. But that's the idea, okay? And it should make sense. If you take the endpoints, no matter how it curves, there can be more than one, but the tangent slope, which is the derivative, somewhere along this point has to be the same as the slope between the two endpoints, okay? Now, one of the implications is this. So if you're traveling in a car at 50 miles per hour and you pass a police car 4 minutes and 5 miles later, you pass another police car still traveling at 50 miles per hour. The next thing that you know, the second police car stops you and nails you for speeding. How can he prove that we were exceeding the speed limit of 60? So think about that. All right, so let's do an example. For the mean value theorem, sorry, before I start, you do need to show certain conditions exist, just like we did on rolls. So same idea. You have to show that the original function is continuous on the closed interval, and you have to show that it's differentiable. Now, you do not show that your two y values are the same, because they don't have to be, okay? And then you're going to do the calculus, do the math, to find where that x value is, okay? So this, it is an existence theorem because it says this exists, but this is actually a working theorem, okay? Just like Rolls was. So on number 6, they give you this function and they show you a picture. So I can kind of illustrate what this idea means as we do the work. So this says if we have from 1 to 5, so here's 1 on the graph, to 5 on the graph. Here is the secant, okay? So I'm going to... Somewhere, as I draw my tangent lines, somewhere this slope has to be exactly the same as this line. Well, it kind of looks like right here, okay? This is my guess. If you look at this tangent line, it kind of looks the same. It's maybe like a little bit over here, but that's the idea. Okay? So let's prove it. We only care about 1 to 5. So f of x, we can plug in any number we want from 1 to 5 because 0 is the only one that can't. So is continuous on 1 to 5. F of x. Well, if I take the derivative, I don't have any sharp points, so even just by my graph, I can tell that it's differentiable. Because remember, sharp points, that's the only, or holes, that's where it's not differentiable. So we could say is differentiable on 1 to 5, because I don't have any sharp points. Okay, I don't need to find the derivative yet. So then I can actually go straight into the mean value theorem. So f prime equals f of 5 minus f of 1. We plug in the slope. So y minus y over x minus x. X minus x. So I'm going to have to take this derivative. So the derivative of 3 is 0. I'm going to write it over here. So f of x equals 3 minus 5. And write this as a power rule. Otherwise, you have to do a quotient rule. So our derivative is 0. Bring down our power. So 5x to the negative 2. And then we need to plug in to find our slope values. If we plug in 5, I get 3 minus 1, which is 2. Plug in 1, which is 5. 5 divided by 1 is 5. So 3 minus 5 is negative 2. All over 5 minus 1 is 4. So 5 over x squared equals, will that be a plus? So 4 divided by 4 is 1. To solve, I'll multiply. So 5 equals x squared, and take the square root. So x equals plus or minus root 5, which is about 2 point something. We're only on 1 to 5, so I really only care about the positive root, okay, because of the domain restriction, which I said root 5 is between 2 and 3, and so yeah, that was a pretty good guess, okay? So we found it. That's our C value. You typically don't have to find the ordered pair because they just want to know the x value where it occurs. All right, number 7. Find the equation of the tangent line. So remember that's y minus y1 equals mx minus x1 to our graph at the point that is the solution of the mean value theorem. So I'm going to need to do the mean value theorem. Because we're just finding something, we should check though, because it might fail. Well, we can plug in any number we want, so it's continuous. When I do the derivative, it's just 2 cosine. That's all continuous too. So our derivative is 2. The derivative of sine is cosine. And the derivative of 1 is 0. And then we're going to plug in f of pi minus f of 0 all over pi minus 0. So 2 plus cosine. All right, so I'm going to do my work here. So f of pi equals 2 pi plus sine of pi. It's in the original, plus 1. So sine is 0. So that's 2 pi plus 1. All right, so 2 pi plus 1 minus, if we plug in 0, we get 2 times 0 plus sine of 0 plus 1. So 0 plus 1. All right, all over pi minus 0 is pi. So 2 plus cosine equals, the 1's cancel. 2 pi over pi, the pi's cancel because they're being multiplied, so we get 2. So to solve this, we're going to subtract 2. So cosine, I'll write up here, cosine of x equals 0. And so now we need to solve this. So if you go to your cosine wave, we only care about 0 to pi. So we want to know from 0 to pi, which is right here, where does cosine equal 0? Well, it's right there. So that's pi over 2. So x equals pi over 2. Okay? So what we're really trying to find is the equation of the tangent line at x equals pi over 2. All right, so we need to find the y value. We're going to plug that into the original. So f of pi over 2 is 2 times pi over 2 plus sine of pi over 2 plus 1. Because we need a y value and we need the slope. The 2's cancel, so I get pi. The sine of pi over 2 is right here, so it's 1 plus 1. So our y value is pi plus 2. So we've got the ordered pair, pi over 2, and then pi plus 2. I know this looks weird, but that's just what it is. So now we need to find our slope so we can use it. So the slope is the derivative, which is right here. So I'm going to label it. So slope, we know, is 2 plus cosine of x. So 2 plus cosine of our x value is pi over 2. Well, the cosine of pi over 2 is 0. So 2 plus 0 gives us 2 as the slope. Okay. I know this is a lot of review. So the equation of our tangent line is y minus our y value equals m x minus our x value. This is what they want. This was a lot of work, okay? I picked a trig one just for more trig review. Due to time, this probably would not be trig, but I think good review. All right, and then the last one is another trig. So I'm just picking trig to give you more trig review, not because these theorems are heavy on trig. They're not. They're a lot easier because they're usually polynomials. So I'm doing harder examples with you in the notes. This one, we're going to have to use a graphing calculator to solve, okay? So make sure you are using a graphing calculator, not Desmos. If you're taking the AP exam, you need to be able to solve on a graphing calculator. You will not be able to use Desmos on the AP exam. We don't really have to guarantee it, but cosine's continuous. The derivatives are sines. Sines are continuous, so it's differentiable. So we've got f prime, which our derivative is, the derivative of cosine is negative sine, so negative 2 sine. And then the derivative of cosine is negative sine. The inside stays the same, times the derivative of the inside. But that 2 is going to go in front, so I'm going to write this nicer. All right, and then we're going to do f of pi minus f of 0 all over pi minus 0. So, f of pi would give us 2 cosine of pi plus cosine of 2 pi. So, cosine. All right. The cosine of pi is negative 1, so negative 2 plus the cosine of 2 pi is the same as cosine of 0, so 1, so negative 1. F of 0 is 2 cosine of 0 plus cosine of 2 times 0 is 0. So the cosine of 0 is 1. So 2 plus 1 gives us 3. So we get negative 2 sine minus 2 sine equals, what is that? Negative 1 minus 3 is negative 4 over pi. Okay, so what we need to do is, because we want to know where they're equal, let's get back to here. I'm going to put this side of the equation as y1 and this side of the equation as y2, and we can find out where they intersect, okay? We're still on the interval of 0 to pi. So that's what we're going to type into our calculator. So go to your y1, and you type in the left side as first equation, and the right side as the second equation. For our domain restriction, we only care about 0 to pi. So make sure you're in radians. Well, we're going to go to our window, and I'm just going to change my x values to 0, and then I'll come down here, and we just change it to pi. Okay, so then we only care about how many times it intersects on this window. Don't worry about the y values. We might have to make this higher or lower, usually not with trig. It just depends. So let's look at our graph. Hold on, I did something. Oh, did I hit a negative? Oh, I hit minus because I was on my computer. So then I'm going to go down to this one and we're going to hit minus 2. I used my keyboard. Okay, so graph. Okay, so this is from 0 to pi. So one of the curves is blue on mine and the other curve is red. So we actually have 2 answers where they intersect. So we're going to find the first one. So we're going to use the calculate feature. So second calc, and we're going to do intersect. So 5. So it's going to say, hey, move your cursor on to where you think it crosses on the first curve. So we're going to move this. I'm just going to pick this one and then hit enter. Then it actually did jump it to the red curve and it said, hey, where do you think it crosses? And it kind of moves it where it does. And then you hit enter again. And so remember, go to 3 places minimum. So 1.748. And write that down. Then we need to find the other one. So second calc, we're going to do intersect again. It only finds one at a time. And so now we have to move our cursor over to this one to tell it, it finds the closest. And so we say, hey, we think it's like there. So hit enter. It jumped it to the red curve, hit enter. And then we guessed enter. And it says, yep, at 0.217. So those are our answers. We found more than one answer, and that's okay. So we get X. You have to be able to solve on a graphing calculator, and that's one way to do it. And 0.217. And that's it. All right, so go ahead and give yours a try, and let me know if you have any questions.